OneClass's online math session. My name is Bassam. I'm an engineering graduate, and today we're going to go through some sample questions that you guys have submitted, as well as other questions that are popular in the subject of math. So let's get started here. Okay, so the first question that we have here, just give me a second here. Okay, so the first question is asking us find the standard form of the equation of the specified circle given the center -7 and 9. So it's giving us x and y coordinates with a radius of 17. So our givens are the coordinates -7 and 9. And we know that the radius is equal to 17. Okay, so knowing this, the main equation we need is the equation of a circle in a coordinate system. And this equation you probably should memorize to answer this question. So the equation follows the form x minus h squared plus y minus k squared equals r squared. And here x and y are just the x and y variables, and h and k are the coordinate variables for our circle. So h and k is what we're going to substitute in. So just looking from this equation, it's coming to be straightforward of what we have to do here. So our equation would follow the format of x minus h, which is the x coordinate that's given for the circle, which is -7. -7 all squared plus y minus k. In this scenario, this would be 9. Equals 17 squared. So to simplify this further, we have x plus 7 squared plus y minus 9 equals 17 squared. So you can expand out the squared. So 17 squared here is 289. But essentially, this is the standard form of the equation for a circle with those given values. So the coordinates -7 and 9. So here, let's look at the answer submitted. It looks like they're asking for a PDF. So just leave a comment. I don't see a PDF. No PDF. No solution present. Format of standard equation of a circle is x minus h squared plus x minus k squared equals r squared. Solution is, as we solved, x plus 7 squared plus y minus 9 equals 17 squared, which equals 289. Okay, so here the solution is not correct. There's no solution, so we provided the correct solution. I'm just gonna clear the page here. Okay. So our next question is asking if the length of the diagonal of a rectangular box must be L, what is the largest possible volume? So when it's asking for largest possible, right away this is telling me that this is an optimization problem, So most likely we're going to be using derivatives. So we can draw a simple coordinate system just to represent our box. It looks something like this. So this is the coordinate system where we have Z, X, and Y. And we have to figure out how do we find the largest possible volume for a given value of L. So L would be from the diagonal, so it would be from the origin to this point of the box. So it would be coming out of the page here, and it would be, I'll just make this in red. So from the origin to this point. So I'll make a bigger box just so it's a little more clear here. So if we had a giant box, oops. Like that with, so this is just a larger image, so this is just expanded out into this bigger box. We're saying from this point to this point is our L value that we are trying to find the largest possible volume, like the value of L when it's the largest possible volume. Okay, so to start off, we would want to define some values for what the volume is in terms of x, y, and z, and the value of L in terms of x, y, and z. So we know volume is 2 sides of the square times the height. So here in a coordinate system, volume would just be equal to x times y times z. So this is just each length of the box times itself to give you the volume. And then the length of L for any kind of point in space from the origin, it follows the format that the length, so here the red line, L squared is equal to x squared plus y squared plus z squared. So this is for any point in a plane. So L could be any other point in a 3D plane or a 3D coordinate system. And it would be in this format. L squared equals x squared plus y squared plus z squared. And that gives us what the value of L is if we square root the x squared, y squared, and z squared. So here we can go one step further and say that L is equal to x squared plus y squared plus z squared. And from this we can kind of substitute the value of z into the value of the volume. So volume, we have one equation here. We have one equation, and then we have another equation. So we want to substitute them into each other to kind of find an equation that has all the variables in one equation. So we have here volume So volume is equal to, so we're going to substitute here z, and we're going to use this equation to find what z is. So if we rearrange it, this would give us z equals L squared minus x squared minus y squared, all square rooted. So here we'd have x times y, and then z is this value right here. So it will be square root of L squared minus x squared minus y squared. I'm just going to draw a line so you can see that these are different. Okay. So now we have the equation that we will be optimizing. So we're optimizing for volume. I believe it said the largest possible volume. So we're looking for the largest possible volume here. So the first step here is we would take the derivative with respect to x, and then we would take the derivative with respect to y, because these are the two variables left in our equation. So here the derivative with respect to x is equal to, so here we can see that it's kind of a complex formula, so we would have to kind of use the product rule, which is the derivative of the first. So there's two components to the volume, this component and then this component. So we say the product rule is the derivative of the first, so xy, times the second, plus the derivative of the second times the first. So we'll go through this step by step. So here we would say the derivative with respect to x for the first term is just y. And then that will be the derivative of the first, and then times the second, which is just what's given above, L squared times x squared minus y squared. Sorry, L squared minus x squared minus y squared, square rooted. And now this is the first component of the derivative, and then the second component is the derivative of the second. So the derivative of the second part, the L squared minus x squared, which is it's a little more complex, so we'll leave that as so plus, and we'll do that in a second here, and then it will be times the first. So we would multiply whatever the derivative is of the second component with xy, which is the first. So let's just think about what the derivative of this is, the second component is. So we would have to use the rule of kind of the derivative of the outside times the derivative of the inside, because we have the square root. So to simplify it, we know that the square root of x, the derivative of that is 1 over 2x. So we know this is true for a simple just square root of x. So this is just something you would have in a derivative table, or you'd have already memorized. So knowing this, so the derivative of the outside component, so the square root, would be 1 over 2 square root L squared minus x squared minus y squared. So we have this component, and then times the derivative of the inside here. And the inside is L squared minus x squared minus y squared. So the derivative here would be negative 2x, because that's the only, we're doing derivative with respect to x. So it will be times negative 2x. So I'll just put this in bracket. So this is just a multiply sign. So I'll put a dot for multiply. And then we can see that the 2's cancel out, and we are left with negative x over L squared minus x squared minus y squared. So this just gives us the derivative with respect to s. So just to clean up this line, we're going to clean it up to put in the final format. So v prime x equals, we have the first component, y square root L squared minus x squared minus y squared, and then minus, so this, so we have this left. So we have minus, we have the two x's, so x squared, and then the y, and then the bottom is right here. So we have L squared minus x squared minus y squared. And we kind of cleaned it up. So let's erase the top here to continue with the solution. We'll leave the equation on the bottom because we'll need that for later. Okay, so now we found the derivative with respect to x. We want to put it in a format that's kind of in one unit, so we can find the common denominator and just combine these two terms. So we have vx prime. The common denominator for this is just this. So we take this denominator and multiply this component by the same. So we'll multiply both the bottom and the top by L squared minus x squared minus y squared, and L squared minus x squared minus y squared. So we'll multiply the first component by this to find the common denominator. So we'll do that right here. So we know the top will be, because we're multiplying square roots, it'll just be bracket L squared minus x squared minus y squared. And then the bottom will just be the same. Square root L squared minus x squared minus y squared. And we also have the term here, so it will be minus x squared y. Okay, so sorry, that's not really on the screen here. Minus x squared y. Okay, now we're going to put all of this together, so it will be equal to y bracket L squared minus 2x squared minus y squared. And the denominator would still be the same. L squared minus x squared minus y squared. Okay. So we found the simple format kind of for the derivative with respect to x. So here we would do the same thing, find the derivative with respect to y for the same initial equation. So our initial equation was, let's see here. So our initial equation was this equation right here. So we're going to do the same thing, but we're going to take the derivative with respect to y of this equation. Okay, so we'll end up with, so we follow the same idea. So the derivative of the first times the second plus the derivative of the second times the first. So you can see that it'll end up being a similar format to this, with the y and x's switched around because the y and x in both terms are in a similar power. So here we would have the derivative of the first, which is y, times the second, plus the derivative of the second, which we said is derivative of the second here will be what we'll do in a second, and then times the first, so xy. So we did the same thing, so we do the same thing here. So the derivative of square root L squared minus x squared minus y squared. So we're trying to find the derivative of that with respect to y. So we know the format that this is, the derivative is 1 over 2 square root y. So knowing this, we'll do the derivative of the outside, which is 1 over 2 square root L squared minus x squared minus y squared, multiplied by derivative of the inside component. So it would be multiplied by negative 2y. So the 2's cancel out here, and then we're left with vy prime is equal to y L squared minus x squared minus y squared minus the second component, which is y squared x over L squared. So we'll combine both of these terms to get just one component, one term in the derivative of the volume with respect to y. And we'll end up with the following. So we'll end up with x all squared minus x squared minus 2y squared with all squared minus x squared minus y squared. So this is kind of the derivative of the volume with respect to y. Now that we've completed this step, so we have this equation, and then we have this equation, which are the two important equations that we need. Okay, so I'm going to clear the page here. Okay. So to maximize the volume, we need to set one of these derivatives to 0. That way we know where the value of where the values or the terms x and y exist, such that it's maximized or minimized, and we'll find this out in a second. So we'll set y L squared minus x squared minus 2y squared. So the derivative of volume with respect to x, we'll set this to 0. And then we'll we know that we can just multiply out the bottom, so and we can we see that at y equals 0, we can't have that as a solution. So if we had y equals 0, then the volume would just be 0. So we have L squared minus x squared minus 2y squared is equal to 0. So we multiplied both sides by the denominator, and we've got rid of the y because at y equals to 0, the volume would just be 0. So we want to see what the volume would be when we look at this component and we set this component to 0. Okay, so this is kind of our first equation. So L squared minus x squared is equal to 2y squared. So we'll call this equation 1. And then we do the same thing for the derivative of the volume with respect to y. So we have x L squared minus x squared So actually, this is the opposite. This is the derivative with respect to x, and this should be the derivative with respect. Here, let me clarify that. So the first component is the derivative with respect to y, and then the second component is derivative with respect to x that was set to 0. So here we have y times L squared 2x squared minus y squared equals 0 over this. So the same square root, same idea here. I'm just not going to write that out because we're just going to multiply by it on both sides of the equation, and then we know that y equals 0, same as above. When x equals 0, the volume is 0, so we would not have a maximum. So here we are left with the equation that we want to maximize. So we're left with L squared minus 2x squared equals to y squared. So this is our second equation. So now we substitute equation 2 into 1, and we'll have L squared minus x squared minus 2 L squared minus 2x squared equals 0. And then we're just going to try to solve for x in this scenario. So we have just have negative L squared, and then we have negative 3, and we have actually, so here we have L squared minus 2L squared, which is negative L squared, and then we have negative x squared minus negative 2x squared, so that would be plus x squared. Oh, so actually that would be 4, so positive 4x squared plus negative x, so that would be 3x squared. equals to 0. And now we have the first kind of solution of our problem. We have 3x squared is equal to L squared, and then x is equal to, so we'll divide both sides by 3, so we'll get L squared divided by 2, but sorry, we'll get L squared divided by 3 on this side, and then we'll also square root this to get rid of the squared, so we'll square root both sides, so if we had x squared, we'll square root x squared to get x, so this will give us L over the square root of 3. So that's the value of x. So we'll clear up some space here. We'll leave the important equations. So now we plug in the value of x in equation 1 or 2. So let's say we plug it into equation 1. So we'll say L squared minus L over square root 3 squared equals 2y squared. And now we get, so if we said L squared minus L squared over 3 equal to 2y squared, we'll get 2L squared over 3. So we're taking 1L squared minus a third L squared equals 2y squared. And then we know y squared is equal to L over 3. And then knowing this, we'll know y squared, sorry, we have a squared here as well. We know y will be equal to L over square root 3. So I'm just gonna, I'll just erase this right here. So this is our equation 1. We know that y is equal to L over square root 3. Okay, so we have the value of y and x where the volume is a maximum. So let me just clear the board here. So when x equals L over square root 3 and y equals L over square root 3, we get a maximum volume. So we go back to our original equation for z. So z equals L squared minus x squared minus y squared to find out the equation for z, because that we still need that component to solve for the volume. So we know here square root of L squared, and then we have L squared over 3, and then L minus L squared over 3. So here we have, if you ignore kind of the L squared, because they're the same for each component of the term. So here we have 1/3 L and another 1/3 L being subtracted from L squared, so 1 whole L. So 1 whole L squared minus a third L squared minus another third L squared will leave us with a third L squared. So we're left with square root L squared over 3, which will give us L over square root 3. And that's the value of z where the volume is maximum. So we know previously volume is x, y, z. And we can see that x, y, and z equal the same value for the maximum volume. So we'd say L over root 3 times L over root 3 times L over root 3. This would give us L cubed on top. So L times L tells it. And on the bottom we have 3 times the square root of 3. So our question is, if the length of diagonal rectangular box must be L, what is the largest possible value? So we've finally gotten to our last solution. The volume is equal to L cubed, with over 3 square root of 3. So we've classified the maximum volume in terms of L, and that's what the question is asking us. So we followed the same format to the solution presented. This solution is correct, and it follows the correct way to find the maximum volume. Great job. Solution is correct. Okay, so we're going on to the next question here. So here it's asking us, we're looking at the square root 1250. There's a typo in the question, but we're looking at the square root of 1250, 1250. And we're trying to look for the simplest radical form, which remains underneath the radical. So what value remains underneath the radical in the simplest radical form? So looking at this, we want to think of factors of 1250. So 1250 is a big number, so we want to split this up to make it easier for us to find the factors. So we can look at the zeros. Zeros are always easy to split up, so we'll say the square root of 125 times 10. So we're looking at 125. We know that 5 times 5 is 25, and then 25 times 5 again is 125. So, 5 times 5, so square root of 5 times 5 is 25, and then if we multiply 25 by 5 again, we'll get 125, which is this term. And then we still have the times 10. So right away, we can see that we have 5 times 5. We can take this out to the front. 5 square root 5 times 10. And now we can also split up the 10 into 5 times 2 to get an identical 5 term underneath the square root. So 5 square root 5 times, and 5 times 2. Sorry, not 5 times 10. 5 times 2 equals 10. So now we have 2 5s, so 5 times 5 is 25. The square root of 25 is 5, so we can take that out in front. So we have 5 times 5 square root of 2. So we just took out the 2 5's multiplying each other from underneath the square root to the front to be multiplied by the already existing 5. And now we have 25 square root 2. And we can say that the value in the radical, the value that remains under the radical in the simplest radical form is 2. And we can't really simplify 2 any further. The only factors of 2 are 1 and 2, so we can't really simplify that. So let's look at the solution here. So here the solution says goes through a similar process. So here they're trying to get the simplest radical form, but they're overcomplicating it here, and they don't really give us the correct answer. So they get the 2 here, but they don't really simplify it into the final form, which is 25 square root 2. So incorrect solution. Incorrect solution used. Student used over complicated process. The correct simplified radical form is 25 times square root of 2. Therefore, the answer is 2 remains under the radical in the simplified form. Okay, so we've given the correct answer to the student. So solution is incorrect. Okay, so our next question is asking the measure of arc PQR is equal to 250 degrees. The measure of arc PR is equal to 110 degrees. What is the measure of angle 2? So it's giving us an image here. Let's save this image. Take a look at what this image is telling us. So here, the image is telling us, so we'll just draw this out so we can have it. So this is the image. So angle 2 is referring to this angle, and we have a circle PQR, and it's providing us with some angles. So this is a submitted question. So here, I'll draw the question again. So here we have, here is angle 2, and then we have a circle that looks something like this. There's a point of contact here, point of contact here. Just to double check, PQR. So this is point P. We have Q over here, and then we have R. So it's giving us the angles between PQR. So we had a dot here. This is the center of the circle, the midpoint. And then we have kind of over here, we have this angle is 250. And the other angle, PR, so this side, is 110. So we have the circle, one side, PQR is 250 degrees, the other side is 110. So we can see that 110 plus 250 gives us 360, which is the full circle. That's the full angle of the circle. So we will erase that. It's asking us to figure out angle 2. So let me draw a more clean diagram below it. So we'll say here we have 2. We have a point here. We have a circle. Then we have another point. We know this angle is 110. Okay. And we want to find angle 2, which is over here. So this question requires us to kind of use equations that relate angles to one another. So we can draw a straight line right down the middle. And we can see that this side over here has a right angle, and this side over here has a right angle. And we've split up the question into kind of two triangles. The value of one triangle, so if we add up all the angles of one triangle, we'll get 180 degrees. Right? So each triangle, if we look at each angle of the triangle, if we add up each angle, we'll have 180 degrees. So we know the first triangle, we have one value over here. This is 90 degrees, and then we also have 90 degrees over here. Since the triangles and the angles are connected, we can kind of look at these two have 90 and 90. The total will be 360 degrees for both triangles. And we already have 90 and 90 on each triangle, so we can just subtract 180 from this, and we'll end up with 180. And we know that the final two angles, so the final two angles in our diagram, this angle and this angle, need to add up to 180 degrees. Otherwise, the triangle rule, where each angle of the triangle equals 180, would not be kept. Because we already have defined that two angles are 90. So we're left with the last two, so angle 2. So angle 2 plus the value we already know, 110, is equal to 180. Based on just kind of thinking about the relationship between angle 2 and the circle and the given values. Okay, so just to repeat it one more time, we have a 90 angle over here, and another 90 angle over here. So these are left, this leaves us with 180, so 90 plus 90 is 180, and then we're left with two components. We split up the diagram into two triangles, so two triangles, each one 180, gives us a total of 360. We subtract 180 because we know two angles, the right angles are 90 each. We're left with 180, so the final two remaining angles need to be added up to 180 to maintain the triangle rule of all angles added will equal 180. So here angle 2 plus 110 equals 180, so angle 2 therefore will equal 180 minus 110, which is 70 degrees. So here it's giving us, there's no really attached file. So here, no solution present or file attached. The correct answer is angle 2 equals 70 degrees. Okay, so here the solution is incorrect. Okay, so on to the next question. Given the right triangle FGH having a right angle at G, so we're giving a right triangle, we'll define F, G, H, and it's telling us at G there's a right angle. What is the value of cotan and the angle FHG? So the angle FHG is this angle. So we'll say this is theta. So cotan of theta is equal to what? So this is, to know how to answer this question, you need to know SOHCAHTOA, and you need to know what is cotan. So let's start off with SOHCAHTOA. So we know SOHCAHTOA. There's just a mnemonic that tells you sine theta will equal opposite, so the opposite side, divided by the hypotenuse. So if we were just to look at this diagram for the angle theta in the diagram, the opposite would be GF divided by the hypotenuse would be HF. Similarly, cos is equal to adjacent over hypotenuse, and then tangent is equal to opposite over, TOA is opposite over adjacent. So this will be tangent of theta is equal to opposite over adjacent. Knowing this, so we know tan is equal to opposite, so tan theta equal to opposite over adjacent. We know this will be useful in answering this question. We need to relate tan theta to cotan. The cotan is known to be the inverse of tan. So just defining cotan here, theta, is always the inverse of tan. So it would equal 1 over tan theta. And that's just the definition that you should just memorize. So cotan theta is equal to 1 over tan theta. So knowing this, we can right away see, okay, we have tan theta defined. We can kind of just substitute it into the cotan theta equation, and we find that cotan is adjacent over opposite. So the opposite side, so we have adjacent side over opposite side. So here, let's erase this. So we need to define cotan theta in terms of the diagram given. So we can say that cotan theta is adjacent, adjacent. The adjacent side is GH, So GH over here. And then the opposite side is FG divided by FG. And that's kind of our solution for cotan of the angle FHG. So whenever we have an angle FHG, as defined here, we're looking at the coordinate H, and we're looking at the angle that I've specified in the diagram, theta. So looking at the solution provided, given the FG, so they've driven out a diagram. So this, we use the same diagram. So this is given in the question. Cotangent of an angle is defined as length of base over the length of the perpendicular. So yeah, so the length of the adjacent over the opposite. So they have therefore cotangent is FHG. So cotangent equals GH over FG. So the answer is correct. Okay, so we're looking at the next question. So if x squared plus mx plus m is a perfect square trinomial, which equation must be true? So it's giving us 4 options, and we're looking at a perfect square trinomial. So some background on what a perfect square trinomial is, so we can kind of just take some examples here. So let me just erase that real quick. So if we had a plus b squared, we would get a squared plus 2ab plus b squared. So this is a perfect square, and then trinomial just means the 3 terms here. So we can also look at the opposite case, so a minus b also gives us a squared minus 2ab plus b squared. A simple way to calculate this is, so we know that the first term will be squared, so a, and we'll get this. Then we know the last term will be squared, so we'll get b squared. The middle term, you just take 2 times a times negative b, and you'll get the middle term. You can also just go through the long process of doing a minus b times itself and just factoring out and simplifying and adding terms together. Okay, so we've gotten some background on the concept here. So we're given 4 options, and we need to see which one gives us such that we have x squared plus mx plus m. So this term and this term are equivalent. That's what we're looking for when we expand each option. So when we expand x minus 1 squared, x plus 1 squared, x plus 2 squared, and x plus 4 squared. So we know that x, let's just go through one by one. X minus 1 squared is equal to x squared, so the first term squared, and then minus 2 times x times 1, so minus 2x, and then the last term squared plus 1 squared, which is just 1. Okay, so we can right away see that option A is not correct because this term and this term are not equivalent. Okay, let's go through option B. X plus 1 squared is equal to, so the first term squared, x squared, and then 2 times x times 1, which would give us 2x. So in the first one we did 2 times x times negative 1. In the second one we'll do 2 times x times positive 1. So that's why we got a negative in the first and a positive in the second. And the last term would just be 1 squared. So just to give you a better description of why it's 2 times x times 1, we can just kind of expand it out the normal way, or the long process. So we can see that x plus 1 times x plus 1, so x times x is x squared. X times 1 is 1x, so it would just be x. And then 1 times x, so 1 times x is x. And then 1 times 1 is just 1. So you can see how it gives us the final. We're just using kind of a shortcut to get the middle term. Okay, so you can see that the 2 and the 1 are not equivalent, so it does not follow that format. Let's go through option C. So we have x plus 2 squared equals x squared plus 2 times 2 times x, so 4x, plus 2 squared. 2 squared is just 4. So we'll erase this. 4. So we can see that 4 and 4 are the same. So we can see that it follows this format, m and m. So m here must be equal to 4. So we'll say this is the correct one. And let's just do the last one to just double check that no other solution is correct. So we have x plus 4 squared equals x squared plus 2 times x times 4, which is 8x, plus 4 squared, which is 16. So here, 8 and 16 are not equivalent. Therefore, the correct option is C. So they give you here in their solution, the student gives the definition for the perfect square trinomial. They go through each step, so they say A is incorrect, say B is correct. So here where they get x squared plus 2x plus 1, so they get the same output as us, but for some reason they say it's true. And then C is not true. So C here is the correct answer, and the solution here provided is incorrect. So incorrect answer choice. The correct answer is C. Student follows correct process but misselects final answer. All right. Let's go on to the next question. So here we're asked a box with a square base and open top must have a volume of 8,000 centimeters. So this is probably a typo. It should be 8,000 centimeters squared. Find the height of the box that should be used to minimize the amount of material used. So we have two terms that we need to define. So we have volume is equal to something, and then we have surface area is also equal to something. And we're trying to minimize the surface area and find the height of the box. So we have a term h that we need to find the value for when the volume is 8,000 centimeters squared. So to start off, to define the volume, it's the base, the area of the base times the height. So the area of the base, since it's a square base, it would be x squared, and then the height would just be h. So I'll just draw a diagram. So we have some box. So we don't know the height, but we know the base is x times x. So x times x is x squared times the height gives us the volume. The area, so some information given in the question, it says it's an open top. So there's no area on the top. It's only the four sides and the base that we're calculating. So the area of the box would be x squared. So that's the base. And then we have to add 4 times each side of the box, so x times h. So now we've derived two equations based on the information provided in the question and defining some variables. So now we can substitute the volume given to find the value for height. So here we have 8,000 equal to x squared h. And we're going to isolate for h, and we're going to use h to substitute into equation 2. We'll call this 2, we'll call this equation 1. So h is equal to 8,000 over x squared. Okay, we'll substitute this into equation 2, so we know area equal to x squared plus 4x times 8,000 over x squared. And now we can simplify this even further. X squared plus, so 4 times 8 is 32, so let's say 32,000 over, we have 1x on top and 2 x's on the bottom, so we are left with 1x on the bottom. So x cancels out one of the x's on the bottom. Now we've found the equation for area in terms of x. Now to minimize the surface area, we want to find the value of x, and we take the derivative and set that to 0. So we'll take the derivative. So we'll leave this equation here. I'm going to erase the rest of the board. So 1 second, let me just get that back. I'm just going to erase a bit of the board. So I'll erase this top part. Okay. So the derivative of a is equal to, so x squared, the derivative of x squared is just 2x plus the derivative of 32,000 divided by x. So to look at this with derivative of 1 over x is equal to so the derivative of this is equal to 1 negative over x squared. So this is just kind of a derivative law that you should know. So knowing this, then you know there's going to be a negative sign, not a positive sign. So we get negative, and then 32,000 over x squared. Now we are going to use the denominator of the second term to multiply 2x by x squared over x squared, and we'll get 2x cubed, and this is over x squared, minus 32,000. Now that we've kind of gotten the derivative of the surface area into a format where we can set this to 0, so we'll set it to 0 to find the optimum x value. So here we multiply both sides by x squared, and we're left with 2x cubed minus 32,000 equals 0. And then we have 2x cubed equals 32,000. And then here we have x cubed equals 16,000. You can see that x is equal to 10 square root 16. So because we have 1,000, we know that the cubed root of 1000 is 10, so we put that on top, and then we're left with the 16 term, the square root of 16. We can simplify this even further, because the square root of 16 is 4, so we get 10 times 4, which is 40. So when we have a large square root, or cubed root, oh sorry, this is not, this is incorrect. So we're looking at the cubed root of 16, not the square root. So cubed root of 16. So yeah, you can't really minimize that any further. So we have the x value here. We'll get we can kind of calculate in our calculator, and we'll find, so 10 times the cubed root of 16 will give us 25.2. So knowing this, we can substitute this value into the original equation to find the value of the height. So now at x equals 25.2, we have potentially the minimum of the surface area. So to double check that this is the minimum, we can take the second derivative of the equation and try to see if it's we set it to a positive or negative value. So here we take the second derivative of this equation, and we see that it's 2 plus 32,000 over x cubed. So the first term is straightforward. The second term, you have negative 1 over x squared. So negative 1 over x squared, the derivative of that will be 1 over x cubed. And then you have just the 32,000 on top. So if we substitute 25.2 into the x here, we can just plug this into our calculator. So we have 2 plus 32,000 divided by 25.2 to the power of 3. We'll get approximately 4. So approximately 4. So since this is a positive value, we know that the function that the area represents will be concave up. So when we take the second derivative, we know that if it's a positive value, that means the function that the area represents is positive up, which means that this is a minimum. So the value of x equals 25.2 is a minimum. So when the second derivative is positive, we know that the value for x is equal to a minimum. So we've kind of just double checked that this value is actually a minimum. So we'll clear the board here. So we'll clear the page. We know that when x equals, let me just double check this. So the value we got was 25.2. So when x equals 25.2, we know at this value we get the minimum surface area. So we have the equation height equals 8,000 over x squared. And we know at this, when we substitute x, so 8,000 over 25.2 squared, this gives us, we'll plug this into our calculator, so 8,000 divided by the square root, divided by 25.2 squared gives us 12.6 approximately. So we'll do squiggly equals for approximately. So when the height equals 12.6 centimeters, we know that the minimum surface area is used when the volume is equal to 8,000 centimeters cubed, sorry, not squared, 8,000 centimeters cubed. So looking at this solution, The volume of the box is, from this, we can obtain the surface area of the box volume. So kind of gives a process. It doesn't show a complete solution. We have a file. Let's see what the file says. Go to save. Okay, so the file is just giving us the question. Okay, so here the solution is not present. Solution is not present. Correct description of process. Correct answer is when the height equals 12.6 centimeters. Minimum surface area is used at a volume. So our constraint was the volume needs to equal 8,000 centimeters cubed. So the solution is incorrect. So that's all we had time for today. Hope you enjoyed the questions and the answer solutions. If you have any more questions, you can always go on oneclass.com for your tutorial needs and any homework help, and where you can submit more questions that you're struggling with. Thank you for tuning in, and hope to see you in the next session.